Hello, am I audible?
Yes, sir.
Okay, we are going to discuss today about carbon based nanomaterials. Let us start. What is diamond? What we know in case of diamond, there are this is diamond is made up of carbon atoms, and if you consider one carbon atom is connected with four other carbon atoms in a tetrahedral geometry. Okay, and if you find this bond, then this is sp3 hybridized bond. Therefore, in case of a diamond, there is no free electron. That is why the diamond is a bad conductor of electricity. But this is the hardest substance we know, and the melting point of diamond is 3500 degrees Celsius, and this is transparent to X-ray and has a refractive index 2.45. And if you add some color impurity atom, then it becomes colored, and the density of the diamond is highest. That is why this is the hardest substance known. Now, but if you consider graphite, okay, this is the structure of diamond. Let me again um, describe it. There is one carbon atom that is connected with other four carbon atoms. Okay, and this is sp3 hybridized orbital. If you consider the carbon, the atomic number of carbon is 6, and this we can write 1s2, 2s2, 2p, 2p2. Okay, it means in 1s orbital there are the two electron, and this p orbital there are two electrons. Okay, what we can do, this one electron we can transfer here. Then in these are this is the inner orbital, and these are the valence shell electrons. And therefore what you can say, that there is one electron in s orbital, 2s, and three electrons in p orbital. Okay, that is 2p. By combining these orbital, there will be sp3 hybridization, and there is a formation of covalent bond between the carbon atom, and this is a three-dimensional network, tetrahedrally connected carbon atoms, sp3 hybridized carbon atom in case of a diamond. And if you consider the distance between the two diamond atom, then that is 154 picometer, or you can say 1.4 nanometer. Okay, now let us consider the graphite. Now in case of a graphite, first let me consider, in case of a graphite, one carbon atom, if we can check here, there will be layer of hexagonal unit cell like this. This is one layer, and this is second layer, and so on. Now here is the covalent bonding, no doubt, but between the two layer there is very weak van der Waals forces of interaction. Okay, and these layers can slide easily. If you apply little force, then this layer can slide each other. Therefore, if you consider the graphite, then this is dark gray in color, that is soft, used as a lubricant, and has density this much smaller density as compared to diamond. And this we use as a electrode material in press, etc., as well as we are using in these graphites in pencil lead. Okay, why we are using in pencil lead? Because the between the two layer there is very small gravitational, there is very small van der Waals forces of interaction, and therefore if you apply small force, that can easily broken up, and that is why these are used in pencil. You can write easily using these leads as a pencil. Therefore what we can say, there are the layers. Okay, and in these layers, if you consider two carbon atoms, there is a covalent bond, but between the two layers there is only the weak van der Waals forces of interaction. Okay, these are the layers, and these are the hexagonal layers, and the structure of graphene is totally different. Sorry, graphite is totally different than that of a diamond. That is why the property of graphite is different than that of the diamond. If you consider, these are the one first layer, this is second layer, this is third layer. In this case, one carbon atom is connected with three carbon atoms, and if you check, then this will be sp2 hybridization. Okay, and there is formation of one sigma bond and one pi bond, or you can say this is the acetylene type of bond, or there is one pi bond here which is delocalized. Okay, due to this delocalized, we can say this is only sp2 hybridization. S is 1, p is 2, one electron is remain unbounded, because we know in outermost cell there are the four electrons. Okay, and this one electron can form pi bonds which is delocalized. Okay, therefore there are many pi bonds in case of a graphene. This, therefore we can say this graphite, there is graphite is an allotrope of carbon. Suppose if you consider the carbon in the form of 3D, then that is gray diamond. And if you consider one single layer or layer form, then that is graphite, and electron can easily move in the graphite. That is why the electrical conductivity of graphite is more than the diamond. Okay. But let us suppose this is the graphite. Suppose somehow I separate these layers. Suppose somehow I separate these layers. Okay, and obtain, suppose I obtain a single layer of, suppose a single layer of graphite. Okay, somehow suppose if we obtain single layer, one single layer, that is hexagonal layers. Okay, and there are the delocalized, one delocalized electron, and which increases the conductivity. Then what is the name of this single layer? Can anybody tell me? If suppose we obtain the single layer of graphite, then what we call it?
Graphene.
Haji?
This is the 2D.
Graphene, sir.
Graphene. This is 2D layer. This is two-dimensional layer. Okay. Why two-dimensional layer? Because the, suppose if you consider this is X, and suppose this is, if you consider Y, then along the Z there is only one atom thick layer. Okay, that is very very less than nanometer.
But we are not considered that thickness, no? Oh, okay, sir. Continue.
What I am saying, that there are only two dimensions. Okay, and in third dimension there is no thickness, very small thickness. That is why we call it as a 2D material. Okay, this is two-dimensional material, X and Y, two dimensions only. Along the Z dimension there is no thickness or very small thickness, one atom thickness, one atom thick layers. That is why we can say this is two-dimensional material. Okay, if you combine these layers one by one, then that will be graphite. Okay, but suppose somehow if you roll these layers, suppose if you roll this layer, then this will be like this. Okay, which is known as carbon nanotube. And somehow, if suppose you obtain, or you can, from this sheet you can make a spherical particle like thing, then this is known as fullerene. What I am going to tell you simply, that using carbon we can make other forms of the carbon in the form of either graphene, carbon nanotube, or fullerenes. Okay, this is the graphene, two-dimensional single layer of graphite, and this, from this you can obtain spherical sheet. This अभी
Yes,
तक
sir.
इससे पहले दिख रहा था?
यस
Sir,
सर,
after
थोड़ा
some
बीच में
time
कट हो
before
गया ना
also
सर.
your voice is not audible, sir. Can you repeat
ओके
all?
ओके, नहीं इससे पहले तो दिख रहा था ना, बीच में गड़बड़ हुआ है ना?
No,
After
sir.
2D, yes, sir.
ओके ओके ओके, ये कुछ प्रॉब्लम हो गई है।
Last two to
Yes, sir.
Yes, sir.
yes, sir.
ओके, this is a single layer of graphite, and from this single layer of graphite either you can obtain from graphene single layer of graphite you can obtain graphite, carbon nanotube, fullerene. Okay, what I'm discussing simply that graphene is a single layer of graphite. In case of a graphite, layers are weakly bounded to each other which can slip to each other, and these are the hexagonal carbon layers. And using graphene, we can say if you roll that graphene, if you consider that graphene and roll in a tubular form, then that will be carbon nanotube. And if you roll somehow that becomes spherical particle, then that is fullerene. Okay. But how to obtain? Question is how to obtain single layer of graphite. Can anybody tell me how to obtain single layer of graphite? अगर मुझे सिंगल लेयर ऑफ ग्रेफाइट चाहिए तो क्या किया जाए?
We will do some techniques to want like that layer.
Which technique? Graphene was discovered in 2004, okay, by these scientists, and they separated single layer of carbon, that is from graphite, using scotch tape method. The first they have discovered this using scotch tape method. How to synthesize? Let us consider we have a scotch tape. This is the scotch tape and this is the graphite. We can, this scotch tape means that there is a glue and this will stick to the glue, and this is a substrate where we want to single layer of graphene. Then we will place this on at the surface of this and apply a sudden mechanical force. In this way, here this is the graphite, no doubt this is graphite, but we go on applying this and you will obtain layer by layer, and at last there will be only single layer of graphene at the surface of this crystals, or we can separate single layer from graphite. What is the procedure? Suppose this is the tape and we can stitch some graphite to this. Okay, now this is simply, here is the graphite and this is the substrate. Okay, by applying this over at the substrate, and then we will apply some mechanical force and suddenly apply some mechanical force, and here we can obtain single layer of, if you go on peeling, suppose these layers at the end you will obtain a single layer at the bottom of the substrate here. Okay, they have discovered using this, and for this these two persons were awarded by the Nobel Prize in 2010 for the discovery of this graphene. Okay, this is the scotch tape method. You can use, and on the scotch tape, like here is the graphite, and you go on applying mechanical force, and finally you will obtain single layer of graphite. Okay,
सर इसके लिए कोई स्पेसिफिक मटेरियल यूज करना होता है?
this you have to simply use graphite.
सर मैंने किया था, मेरे को तो नहीं मिला था.
हाँ जी,
सर वो पेंसिल को किसी मेटेलिक सरफेस पे ऐसे घिस करके फिर उस पे टेप लगा के जो उसको निकालते हैं तो भी हमें एक शीट मिलती है ग्रेफाइट
हाँ
की।
तो बिल्कुल मिलेगी। कैसे पता चला तुम्हें कि नहीं मिली?
सर वो ऐसे आ नहीं रहा था ना सर,
कैसे
मतलब
आया तुम्हें, कैसे पता चलेगा कि बन गई?
सर मैंने जितना भी इंफॉर्मेशन देखा था उसके बेसिस पे मैं
क्या
जज
ऐसे
कर रहा
कोई इंफॉर्मेशन नहीं है? दिस यू हैव टू टेक रमन स्पेक्ट्रा or TM spectra, etc. Then you can tell that yes, this is single layer of graphene. Okay.
Sir, excuse me, sir.
Yes.
Sir, this graphene material is the nanoparticles, na?
Yes. Surely these
Sir,
are the nanomaterials.
how we will tell, like looking our naked eyes, this is the like a single layer thing.
No,
Due
you
to this,
cannot say anyway. You cannot predict using naked
this
eye. You have to use the techniques as I told you, Raman spectra you have to take, or STM 10. Okay.
sir, but
Using
here
that.
using this is look like a hands, na? Hands and normal tape.
Yes. Go on peeling these graphite layers. Ultimately, you will obtain single layer of graphene. Single layer of graphite, that is graphene.
Sir, this is
And in
normal,
order to
sir, normal tape, or is there any particular tape, sir? This thing.
just normal tape,
Okay.
scotch tape.
Using this technique, this will be following single layer, that
Yes, you
nanoparticle.
will obtain single layer of this, and then you have to use advanced methods to characterize this, that yes, there is single layer on that. Or there are many other methods. Using that method, you can easily synthesize graphene. This is a difficult method because you cannot obtain single layer very easily. But yes, using this method, we can also obtain single layer of graphite.
Sir, due to this method, they are getting a Nobel Prize.
Yes, they were discovered this first and they got the Nobel Prize.
Okay, sir.
And why this graphene is so important? Because graphene is very important. First is first thing is their conductivity is very high. Band gap is zero. If you find the band gap of graphene, that is zero. Okay, it means this is very highly conductive, and graphene also show quantum Hall effect at room temperature. Okay, and the electron mobility in graphene at room temperature is very large, or you can say the conductivity is very high, resistivity is very small, even smaller than silver, or they are the best conductors. And the mechanical property of this single layer is superior than steel. This is 200 times stronger than compared to steel. Okay, single layer of graphene is stronger, 200 times stronger than steel. And this graphene has many applications in many areas of physics, chemistry, biology, and so on. You can apply solar cell, supercapacitor, battery, LED, chemical sensors in screen sensor, and so on, in automobile and everywhere. You can make a nano composite. You can even dope this graphene with other material, and we can modify or tune the property of the graphene as per our applications. Okay. And if suppose if you consider graphene, okay, in graphene there are the dangling bonds at the surface of the graphene, because as we know, in case of a graphene there are double bonds. Okay, and that double bond we can easily break, and then there will be generation of free radicals at the surface of the graphene, and these free radicals of the carbon can easily combine with the hydrogen. Therefore, if you pass the hydrogen gas, these carbon atoms can easily combine with the hydrogen and they form the carbon hydride, or that is known as graphene. Okay. Suppose this is the graphene, single layer of graphite. You can combine hydrogen, and then this hydrogen will attach with the carbon atom, or this there will be the reduction of this carbon atom, or you can hydrogenate the carbon atom, and this will be the graphene. And this graphene will lead to change in the property. For example, if you find the band gap of the graphene, that is 0. But if you find the band gap of graphene oxide, that will be not equal to 0. Therefore, in this way, we can modify the property of the graphene. Okay. Therefore, this is the graphite and this is the graphene, single layer of graphite. And
Hello.
what you can do, yes,
Hel- Sir, in previous slides, you shown that mechanical strength of graphene is 200 times the steel.
mhm.
So how we calculated means what type of apparatus we use to calculate this means because
For
it is
measuring the mechanical property, we you have to use a setup which is known as um, hardness measurement setup, where we can find the hardness of the any material. And because this is single layer and this is almost free from the defect, and if suppose in some material if there is no defect, then the mechanical property will improve. And that is why these nanomaterials have very high mechanical strength. And the mechanical strength, the Young's modulus, etc., we can determine using hardness measurement methods. Okay, this we will discuss later on, but there are methods using that we can find the hardness of the material. And this is the graphite, and this is graphene.
हेलो सर।
And yes,
सर ग्रेफीन के स्ट्रक्चर में सर फ्री इलेक्ट्रॉन होगा ना?
यस बिल्कुल, यही जो इलेक्ट्रॉन है, थोड़ा सा एनर्जी दोगे, ये जो पाई इलेक्ट्रॉन है वो ब्रेक हो जाएगा और फ्री हो जाएगा, और इसमें बहुत
सर
सारे फ्री रेडिकल्स भी बन जाएंगे। एक
एनर्जी
इलेक्ट्रॉन फ्री हो जाएगा, एक इलेक्ट्रॉन यहीं रह जाएगा कार्बन के ऊपर, देन दैट इज कार्बन फ्री रेडिकल्स, एंड वन इलेक्ट्रॉन बिकम्स फ्री. This electron is very loosely bound to the carbon atom because that is pi electron, and that is electron is delocalized over the sheet.
Sir, no band gap means the electrons will be tightly bound, na?
Why tightly bound? In case of a
Because
metal, electron can move very easily because there is no band gap. Similarly, here there is no band gap. If you find the valence band, conduction band, they will they will touch here, and there is no gap, as
it
we
means
consider in case of a metal.
without any energy, it will be moving freely.
They are moving freely, even they are moving with relativistic velocity. If you find, that is why their conductivity is very large, because this
Okay,
is
okay.
very special kind of a system. And electron is confined in 2D layer. Electron has restriction to move along the z direction, and this will lead to very confinement effect, quantum mechanical effect, that will increase the velocity of the electron and mobility of the electron. That will change, exactly, that will change the optical property, mechanical property, electrical property of the material.
Sir, but in solar cells like that, band gap only we will use semiconductor material, not in this conducting material. Due to this band gap low, we can't use this thing to in that material, sir. Only we use
Yes, you are
semiconductor material.
absolutely right. That is why we are considering other materials. For example, we can take graphene and we can add oxygen. Okay, we are oxidize it. This is known as graphene oxide, as we have discussed, also known as graphene. If you okay, let us oxide, don't write is hydride. Okay, then this is graphene, and if you attach oxygen, then this is known as graphene oxide. And here the band gap, there will be some band gap. Okay, by changing the graphene, we can obtain other material where there will be some band gap, and then you can use these material in solar cell, etc. Okay, we will modify the graphene structure. Suppose we can add oxygen. Okay, or suppose this is the graphene oxide, add hydrogen, then at some places hydrogen will be added, at some places there are oxygen, then this is known as reduced graphene oxide, and then there will be change in the properties. Okay.
हेलो सर।
Yes.
सर बैंड गैप जीरो है, इसका मतलब ये थोड़ा ना कि सर विदाउट एनर्जी ये कंडक्शन बैंड में चला जाएगा इलेक्ट्रॉन। थोड़ी बहुत एनर्जी देनी पड़ेगी ना सर इनिशियल
क्यों
में,
देनी पड़ेगी भाई?
क्योंकि क्योंकि
ये
सर एनर्जी
मेटल में
नहीं।
क्या होता है, वैलेंस बैंड एंड कंडक्शन बैंड ओवरलैप्स। ओके,
सर फिर ये बॉन्ड ब्रेक कैसे होगा सर विदाउट एनर्जी?
बॉन्ड ब्रेक की जरूरत ही नहीं है, because the valence band and conduction band is overlapping. Okay, and here we are talking about, if you consider at room temperature, anything you will consider at room temperature, there are large number of free electrons. You are not using graphene at graphite at 0 Kelvin temperature. You are using at room temperature. There is sufficient amount of energy to break this bond. Now, therefore, by oxidizing and reducing, we can obtain graphene oxide and reduce graphene oxide. And here there will be some band gap and there will be change in property, and depending upon the type of the applications, you can use whether graphene oxide, reduce graphene oxide. Okay, in your in laboratory, if suppose you want to use these material in particular application, then using any material you can convert the graphene into any other material, and in this way you can change the property. There is no problem. Now, therefore, if you have graphene oxide, reduce it. If you combine with hydrogen, then there will be oxygen as well as hydrogen. Okay, let us consider graphene, oxidize it, there will be graphene oxide, then again further reduce it, reaction with hydrogen, then this will be reduced graphene oxide. You have to consider graphene, first you have to react it with oxygen and then with the hydrogen. In this way we can modify the property of the graphene. Therefore, diamond can exist, the carbon can exist in various types of allotropes like diamond, graphite, fullerene, carbon nanotubes, and graphene, that is carbon hydride, and graphene, that is single layer of graphite, and there are very others also like graphone. What is graphone? A partially hydrogenated atom of graphene, which is highly ferromagnetic. What is the meaning? That consider the graphene and partially hydrogenate. It means at only some places of carbon attach hydrogen, then that will be graphone, and property will be different than the graphene. And even you can obtain graphene and graphene. Okay, suppose what we know, that in case of graphene there is sp2 hybridization, in case of a diamond there is sp3 hybridization, but we can arrange these hexagonal layers like this in such a way, we can arrange these hexagonal layers, carbon carbon in the form of carbon carbon triplets, and so that we can arrange these hexagonal rings in such a way that there are various acetylene bonds, or the various double bonds are available in such a way that if you consider spn, then this n is greater than 1, less than 2. In between that we can modify, then this structure, like this type of a structure 1 is, this is known as graphidine, and the structure 2 here, this is known as graphidine. Okay, here is the more double bond. Or arranging these hexagonal layers in various forms, we can obtain different types of graphene structures, and in this way we can modify the property of the graphene. Or we can say only single layer of graphite, that is graphene, but this is in your hand, you can modify that and you can obtain the desired property of the graphene. There is no problem. Okay, but you have to do little experiment and you have to prepare this material, and then you have to study that which property is enhanced and why that property is enhanced, and so on, and then you can use this material in various type of applications. Okay, now let us consider Buckminster fullerene, or you can say nano dot or quantum dot. Here, if you roll graphene in such a way so that you obtain this football like structure. Then this is known as fullerene, and this is an allotrope of carbon, diamond you can say, and this is hollow cage like structure. This is empty inside, and if you find, then there will be sp2 hybridization, and there are the 60 carbon atoms. And if you consider, then there are the hexagonal rings, okay, and also there are the pentagons rings like this. And if you consider C60, there are 12 hexagons, and there are 20 hexagon and 12 pentagons. And this can exist in C60, C70, C84, and so on. This generally exists C20 plus 2n, where n is the number of hexagons. Like for example, in C60, hexagon are 20. Therefore, if you 20 into 2, then this is C60. There are the 20 hexagon, 12 pentagons. Okay. Therefore, for the discovery of fullerene in 1996, these three persons, that is Robert Curl, Kroto, and Smalley, these were awarded by the Nobel Prize for the discovery of fullerene, okay, using vaporization of graphite, okay. But this was discovered accidentally. The graphene was discovered accidentally. Oh, sorry, fullerene. Fullerenes were discovered accidentally. Actually, let me read this. Kroto was interested in radio astronomy. Okay, radio astronomy means uh, he was studying that how many carbon molecules are present in interstellar clouds. Okay, that are responsible for signals and so on. So he was studying on carbon species, or you can say carbon clusters, using microwave spectroscopy. Curl, he was and using mass spectrometer they can obtain the mass of the carbon cluster. Okay, they were studying on this, that using this electric arc discharge method or using laser ablation method, we can evaporate the graphite, or and then we can cool that graphite and we can obtain the cluster of carbon atoms. But accidentally they discovered the structure fullerene. Okay, but they were studying long chain carbon molecule, that is carbon clusters, and that may be they met that type of carbon cluster, they might be present in the red giant stars, etc. They were studying astronomy aspect of the carbon in interstellar mediums, but they found that in mass spectrometer there is a very strong peak at 720 mass. 720 means, if you divide with the atomic weight of the carbon, that is 12, then this means 60 atoms. They have found that there are 60 carbon atoms combining to each other, and that this type like this peak is present, and that is most intense peak. It means there in their experiment, carbon is always combining in the form of 60 atoms. And this was very puzzling to them. Why only 60 carbon atom cluster is forming there? Okay. And what is the, this is the most, this is the most available carbon cluster in their experiment. The question is why this 60 carbon atoms were forming in that experiment, and what is the structure of this 60 carbon atoms fullerene. Okay, but they were very puzzled that how we can predict the structure of these, this new discovered material. But as we know, in the beginning of discovery of benzene, there was a problem that suppose if you consider 6 carbon atoms, okay, and if they suppose combine in a linear chain, then that cannot explain the property of the benzene. And in order to give that structure, Kekulé in 1865 he proposed this structure. Oh, yes, that these carbon atoms are not combining in linear chain, but these carbon atoms combine in a form of a in a form of a cyclic structure, or like this, and then he discovered the benzene structure. Okay, can anybody tell me what was the story related to the discovery of benzene structure?
Sir, he got a nightmare in which he saw a snake biting his tail.
आप दूसरों को बताओ, सबको समझ में आना चाहिए बस.
मीन्स उसको रात को सपने में आया था कि एक सांप उसी की खुद की पूंछ को ही निगल रहा था.
Yes, he dreamed that yes, there is a snake, and that is like this. He is bind like this, he eating or something like this structure, and then he uh, after that he thought that yes, these carbon atoms might combine in a form of a ring, and then this was discovered. Same is there. They were these three scientists were very puzzled that what is the structure of C60 carbon atoms. But one of the scientists had visited this place at that time, and then suddenly he recognized this dome like structure. And then this is the hexagon structure. There are the hexagons and pentagons in this structure. And then based on this dome, which were made by the bulk minister Fuller, and then um, using this concept in 1969, this dome was made, and using this they discovered that yes, these carbon atoms must combine in a ball like structure where there must be 12 pentagons and 20 hexagon, so that it becomes a stable structure. And for this they were awarded with the Nobel Prize for the discovery of fullerene. Okay, therefore, but initially it was thought that yes, this must be very unreactive. Why this will be unreactive? If suppose there are 60 carbon atoms and the double bond here, this double bond you can write here, or you can also write here and here. These are known as resonating structures. And if you write the resonating structure, then there will be 12,500 resonating structure. It means it must be very, very stable. But experimentally, it was found that it is not very stable. Okay, because many of the resonating structure do not contribute to the stability of the molecule. Okay, and C60 molecules is not very stable, or this is very reactive, and its reactivity is like alkene. This is not similar to aromatic compound, but this reactivity is like more than alkane and like to alkene. And this can react, this can go any reaction, because this is reactive. Okay, due to presence of this double bonds. And there are various types of fullerenes like 60, 70, 75, and so on. There are various types of fullerenes, and you can obtain this fullerene. Suppose if you consider any polycyclic aromatic hydrocarbon and incident some laser light, and then these hydrocarbon can combine in a form of a ring, and and you can obtain CO2. And if you obtain in a solid form or in a powder form, then this will arrange like this. Okay, and then this is FCC structure, and the edge length is 142 nanometer. If you crystalline, even we can obtain the crystalline form of graphene, fullerene. And these are because very reactive. You can add halogen reaction, you can obtain many derivatives of fullerene, and the properties of this derivative will be drastically different. It means one single fullerene compound, from one single fullerene we can make many other derivatives, and that derivative will be useful in many other applications. For example, you can add halogens, you can you can oxidize this in the presence of light, or you can add some cyclic compound, or you can do some elimination reaction, or even you can add some alkyl group, or you can organometallic compound, even you can make some complex compounds, and so on. Even you can obtain polymerization, nucleophilic and substitution reaction, elimination reaction, and so on. Full arenes, you can add hydrogen, oxygen, and so on. Therefore, using various type of reaction, we can obtain many derivatives of fullerenes, and these derivatives will be very useful in photovoltaic solar cell applications. Okay, because we can change the property of the fullerene, and even these are very useful in as a antioxidant. Okay, because fullerene readily react with free radicals. Okay, which are dangerous to the body. If you consider the fullerene, then these fullerenes are very reactive. They can easily react with the free radicals. Okay, therefore these show antioxidant properties, and their antioxidant properties 100 times more effective than the drugs available in the market. They can easily react with the free radicals. Okay, like oxygen free radicals. That is why they are very antioxidant. Second thing is, because double bond is present in fullerene. These double bonds, for example, there is double bond in case of a fullerene, and this double bond, if you combine this fullerene with hydrogen, then this double bond will break and the hydrogen will attach to this. This is known as hydrogenation, or you can form carbon hydride or graphene. And if you consider graphene, then there will be carbon hydrogen bond and carbon carbon bond. It is very difficult to break carbon carbon hydrogen carbon carbon bond, but is it very easy to break carbon hydrogen bond? What is the meaning of this? You can consider, we can use fullerene for the storage of hydrogen. You can pass hydrogen, that hydrogen will combine with the carbon atom, and that will form carbon hydride. But suppose when you have to use hydrogen, then applying little force, this hydrogen bond can break, carbon hydrogen bond can break, and then you can obtain the hydrogen again. What is the problem of hydrogen? Hydrogen is explosive in nature, and there is a problem of storage, that how to store these hydrogen atoms, because these are very explosive. Then what we can do, we can combine these hydrogens with fullerene, and suppose whenever that becomes stable, if you form carbon hydride, that is graphene, that is very stable, and then we can regenerate these hydrogen from that carbon atoms, and that can be used for the fuel purposes. Therefore, this is an ideal material to store the hydrogen, or this can be used for the hydrogen storage. Okay, and other is, what we can do, suppose this is fullerene, you can do some reaction which is known as ring opening reactions, and you can react these ring, and then there will be the opening, and then in that opening you can add any material, that is known as encapsulation, because this is hollow. Hollow means you can add any material inside, and by adding any material inside, we can change the property of that fullerene further. Suppose you can add some MRI contrast agent, okay, and that fullerene based MRI contrast agent and materials will be highly stable and more effective than the fullerene. Therefore, we can attach, we can do molecular surgery, we can break the ring, we can add any material inside, and then we can use this material as per our application, as per our need. Even suppose this C60 carbon atom is not soluble in water. This is not soluble in water. But what you can do? You can attach some hydrophilic group at the surface of this, and then this can easily dissolve in the water. Okay. And in this way, this will be capable to transport drugs to the various places of the cell. Or this can be used in the drug delivery in the body. Okay. There are the two ways. You can consider this material, suppose, which you have to deliver to the organ, and this is the carbon, and you incident laser light, then there will be encapsulation. Or you consider the graphene fullerene and then do molecular surgery, and then you obtain in the fullerene filled with this material. That is encapsulation. We can do anyway. Okay. But yes, in the hollows of this graphene fullerene, we can add any material. Okay. Therefore, the fullerene can be used in many applications, but even this can be used in cancer treatment. But this is in developing stage. Research are going on how to use fullerene in catalysis, in water purification, as a biohazard protection, for in supercapacitor batteries, vehicles, medical use, and so on. Okay. Therefore, these fullerenes are very useful. Or we can say that by making these nanomaterials, we can use these nanomaterials in various type of applications. Now let us consider carbon nanotubes. Okay. As this is the graphene single layer, you can roll this graphene and obtain carbon nanotube. That will be also 100 times stronger than steel, and conductivity will be very high. Okay. The electrical conductivity will be very high, thermal conductivity will be very less. And this is single wall carbon nanotube because there is a single wall. Similarly, we can obtain multi-wall carbon nanotube. Multi-wall means there is one wall, second wall, third wall, and so on. Several sheet of carbon atoms. If you roll several sheet of carbon atom, then you will obtain multi-wall carbon nanotube. Okay. And if you suppose this is the carbon nanotube yarn, and this is 100 times stronger than human bones, because this is very stronger material. And therefore, if you make the composite of this carbon nanotube with any material, that will enhance the mechanical property of that material. That is why these carbon nanotube nanocomposites are used in making the space vehicles. Okay. Therefore,
Sir,
yes.
sir, in that picture, what is nanotube on that thick one or slim one?
What are you saying?
It is a thread like na, sir.
Yeah, this is carbon yarn. This is thread-like structure. This is not carbon nanotube. This is small nanotubes. They are combined. Suppose 1,000 nanotubes are combined to each other. Then this become nanotube yarn. And the carbon nanotubes of as fullerene was discovered accidentally, similarly carbon nanotube was also discovered accidentally by S. Izima in 1991 using TEM. Okay. He was studying carbon clusters like fullerene. He was studying fullerenes using arc discharge method, and he obtained carbon nanotube. But the carbon nanotubes were so less in the sample that Izima himself said that it was like observing a needle in a haystack. Okay. That was very difficult to observe carbon, because as he was taking the TM pattern, there are only one or two nanotubes. Therefore, it was very difficult. But yes, there were nanotubes. But before the discovery, Smale had already speculated that yes, from fullerene we can obtain carbon nanotube, no doubt. But it was discovered by Izima, and there were many theories at that time that predicting that if you obtain the carbon nanotube, then how the electron will behave and what will be the phonon spectra and so on. And this discovery, that is discovery of quantum, the discovery of nanotube was a breakthrough. And using the setup of fullerene, we can synthesize the carbon nanotube. But the condition little bit we have to change, because the condition at which we are synthesizing fullerene, that is unsuitable for carbon nanotube. In order to make carbon nanotube, we have to little change the condition. If you change the condition, we can obtain carbon nanotube. Even we can obtain the tube form of the many material like zinc oxide, titanium oxide, MOS2, and so on. We can obtain the nanotube form of these materials also, and we can study how the property will change. Therefore, carbon nanotubes are nothing but the cylindrical cylinders made from graphite sheet, and where they are closed at the end. Or you can say that by folding the graphite sheet, we will obtain a cylindrical form. That will be the carbon nanotube. But it is only an imaginary sheet. Actual growth can be different. Actually, we cannot say that there is rolling of the sheet and we obtain the carbon nanotube. No. Actually, the mechanism is different. But for the understanding, we can say that yes, there is a rolling of the graphene sheet, and we obtain carbon nanotube. Okay. And if you roll one sheet, that will be one sheet, that is single wall carbon nanotube. And if you roll 10 sheets, or then that will be the multi wall carbon nanotube. Okay. Therefore, if that are the concentric nanotube, then that is known as multi-wall carbon nanotubes. And the distance between the two wall, if you consider distance between the two wall will be 0.034 nanometer, same as the distance between the two layer of the single layer of the graphite. Okay. And this multi-wall carbon nanotube, this can be observed, we can synthesize easily, but it is difficult to synthesize single wall carbon nanotube. Okay. But if you prepare multi-wall carbon nanotube, then by using etching method, we can obtain single wall carbon nanotube. In case of single wall carbon nanotube, the diameter is ranging from 1 to 2 nanometer. And if you consider the multi-wall, that is 2 nanometer. Therefore, obtain a 2 nanometer diameter of single wall carbon nanotube. Okay. Therefore, this is in case of a carbon nanotube, there is sp2 hybridization. And but this is not correct way to say that yes, we obtained carbon nanotube by folding the graphene sheet. Okay. This is not the correct way to tell. But depending upon the folding of the graphene sheet, there will be various types of carbon nanotube. Let us consider, suppose for example, this is the graphene sheet. You can either roll across this axis, you can roll across this axis, or you can roll across this axis. If you roll along this axis, then structure will be different. If you roll across this axis, structure will be different. If you roll across this axis, the structure will be different. And you will obtain different types of carbon nanotube. For example, if you consider this is known as N0, means along the x direction. And after N, suppose N atoms, N layers, then you will obtain like this type of a pattern. This is known as zigzag pattern. If you roll across this, then we will obtain chiral nanotubes. And if you roll across this, we will obtain armchair carbon nanotubes. And there may be formation of cap at the end, and that may close. And this carbon nanotube you can also synthesize using carbon nano rings, and go on adding these carbon nano rings one by one, and we will obtain carbon nanotubes. And therefore, carbon nanotubes can exist in zigzag structure, armchair structure, helical structure, depending upon from where you are folding the graphene sheet. If you fold at 0 angle along this direction, along the parallel to the x-axis, then that will give you a zigzag pattern like this. Then this is known as achiral nanotubes. Okay, achiral means that mirror image will similar to the original image. And if you consider across this, that is along the 30 direction, along this direction and 30 angle, then this will be like this type of a geometry. If you check, then this is armchair CNT. And if you consider in between 0 to 30 degree, and in this direction, any AB direction, then this will be known as helical CNT. Okay, depending upon the value of R, you are taking an angle, you will obtain different zigzag, armchair and helical type of structures. And these carbon nanotubes, even from these carbon nanotube, you can make ropes, springs, strips, bamboo like structure, conical shape like structure, flower like structure, or any other structure, any other morphology. Okay, using these carbon nanotube, you can make any other bigger morphology, and that will change the property of the nanomaterial. Okay, and this carbon nanomaterial we can synthesize using various techniques. For example, मैं 15 मिनट और पढ़ाऊंगा. Okay, we can synthesize this carbon nanomaterial using various techniques. Okay, but for example, ISIMA first used electric arc discharge method, and he synthesized protein, he synthesized fullerene, but very small amount of multi-wall carbon nanotubes also were present. Okay, but that were very low in number. Using arc discharge method, you can synthesize fullerene, but is it difficult to synthesize carbon nanotube? But we can use other method like pulse laser deposition method or chemical vapor deposition method to prepare single wall carbon nanotube. Because we know electric arc discharge method, which was used by the ISIMA, we can use this to produce multi-wall carbon nanotube. And in order to obtain single wall carbon nanotube, we can use pulse laser deposition methods or chemical deposition method. In this case, what we do, we consider electric charge discharge method, we consider graphite electrode. Okay, and we pass very strong electric field, apply very strong electric field, so that this graphite will be converted into a 3000 degrees Celsius temperature will be generated, and this graphite will be melted, and there will be evaporation of graphite, and there will be formation of CNT and fullerenes. Okay, and from that we can find the multi-wall or single wall carbon nanotubes. For example, diameter will be in this range and of the fullerene, and the tube will be length of the tube will be 1 meter. Using this condition, we can synthesize, like this is the typical condition, that use electrode material as a graphite, what should be the diameter, what should be the gap between the electrode, how much potential we should apply, how much current we should pass, so that we can obtain multi-wall carbon nanotube 30 to 50%. Similarly, we use chemical vapor deposition method. Suppose there is a muffle furnace, here we will place substrate, and then we will pass carbon material like C2H2, acetylene, which is very reactive material. In order to reduce the reactivity, because this is at very high temperature, we use inert nitrogen, and then we using vacuum pump we can remove oxygen, and then we can pass these materials, and in this furnace there will be breaking of this C2H2, and that will lead to the formation of carbon nanotube inside that muffle furnace. Using this chemical vapor deposition, we can produce large scale carbon nanotubes. Okay, by cracking of carbon hydrocarbons using some catalyst, we can easily break these hydrocarbons, and then we can obtain a multi-wall and single wall carbon nanotube uh, of very high purity and of very, you can say, large scale production we can obtain. This is the condition in order to synthesize this material. And one is the pulse laser deposition method. This we consider the graphite here. Then we incident laser light, very high intense laser light, and then this is evaporated, and then we cool it, and then by cooling we can crystallize these vapors into the form of a solid, and then we can obtain the various diameters of single wall carbon nanotubes. Okay, and how these carbon nanotubes, what is the growth mechanism? Actually there is the atom by atom combination, like these combine one by one, atom by atom combination, and finally we obtain carbon nanotubes. Some scientists also think that initially there is formation of fullerene. Okay, then in that fullerene, for example, there is formation of fullerene, and then there is addition of C2 C3, that is dimer and trimer of the carbon atoms. Okay, there is formation of first fullerene, then these pentagons are very strained, and there is the accommodation of C2 and C3 dimers and trimers, and in this way this grow on, and this will form like a tube like structure, and ultimately we will obtain carbon nanotube. Okay, but this is very difficult to tell that which mechanism is operative, or whether there is formation of cap first, for example, there is formation of cap first like this, or there is the first cap is formed and then there is the growth of the nanotube. This is very difficult to say, but depending upon the condition we can say all the combined mechanism may be operative. Okay, therefore depending upon the condition you can obtain either diamond, graphite, nanotube, fullerene, and so on. Even these fullerenes show superconducting property, like the Tc is equal to this much, and by doping means by adding atom inside the hollow cage like structure, even at the surface of that material we can easily increase or decrease the superconducting critical temperature. Okay, even by considering, suppose this is the graphene oxide, let us consider the precursor of bismuth, and place these, mix the two, and then add this solution in hydrothermal autoclave, and then we can obtain the tube form of bismuth titanate, or you can say we will obtain bismuth titanate, graphene nanocomposites. Okay, using by combining the two. Even suppose you can use the CNT, that is carbon nanotube, and taking the precursor of suppose vanadium oxide and applying hydrothermal method, we can obtain flower like nano composite of CNT with vanadium sulfide, vanadium oxide, like this. This is a flower like structure. Or we can say by combining these carbon nanotube with various other materials, we can change the property of the carbon nanotube drastically for various applications. For example, these carbon nanotubes can be used in a biosensor. For example, this is the CNT. Okay, now this CNT we can attach some anchor molecule, like this is the anchor molecules like this, and this anchor molecule, there is a yellow region at this anchor molecules. This can easily suppose connect to the blood. For example, at the surface of CNT we can combine some other molecules which can easily attach to the CNT, and then there is a reactive group which can easily react with the blood, and then this CNT can be used to detect the sugar level in the blood. Suppose this can easily attach to the sugar in the blood. Okay, and this, in this way, this can be used as a biosensor. Biosensor means using this technique we can easily find that how much sugar is present in the blood. Okay, there will be a reaction between this yellow portion and the sugar, and then a signal will be generated, and that signal we will record, and then we can predict that how much amount of sugar is present in the blood. or suppose you can use as a gas sensor. Suppose these are the carbon nanotube material combined with the polyethylene amine, that is a polymer. Using one polymer, we can coat CNT with polymer, and this polymer, we know this polymer can easily combine with carbon dioxide molecules. Okay, and then there a signal will be generated. That signal we will record, and we can predict that how many molecules of carbon suppose have deposited at the surface of that. Or in this way, this can be used as a carbon dioxide gas sensors. Okay, we can easily detect that how much carbon is present, how much concentration of carbon is present at at anywhere. Or even this will be used to detect the poisonous gases. Okay, or even this can be used to detect the carbon dioxide level in the person's breath. Okay, or if suppose there is any respiratory problem associated, then using this sensor we can easily predict. Therefore, using CNT, we can easily use as a gas sensor, as a biosensor, and so on. These two-dimensional materials have unlimited scopes. This depends upon you. You can modify these materials and you can use these material anywhere. Okay, because these materials are not single material. What we know, this can exist in many forms. Look, we can say in various types of allotropes like diamond, graphite, graphene, graphene, graphone. Okay, other structures. Even this can exist as a fullerene, various types of fullerene, carbon nanotubes, and even amorphous carbon. Suppose there is no structure, only the mismatching of these graphene layers. Okay, and their random arrangement. Or there is very distorted like this type of hair. There is some arrangement, there is no arrangement, and so on. Loans delight like structure. Therefore, we can obtain these two-dimensional materials in various forms, and that can be used for the various type of applications. हाँ जी, यहाँ तक किसी को प्रॉब्लम है तो मुझे बताए.
सर जो मल्टी वॉल्ड और सिंगल वॉल नानो ट्यूब था, उसमें सिंगल वॉल को तो हम ऐसे ही रोल कर देंगे ना, वो कैसे मल्टी वॉल कैसे इजी रहता है बनाने के लिए?
मल्टी वॉल में देखो, सिंगल वॉल के लिए आपको एक सेपरेट लेयर चाहिए. जब भी आप कोई रिएक्शन करते हैं, जब भी लेजर यूज करते हैं या कोई और टेक्निक यूज करते हैं, तो एटम बहुत ज्यादा इवेपोरेट होते हैं. एक लेयर बनाना आसान नहीं होता है, वो कई लेयर की फिल्म बन जाती है ना, और रोल भी हो जाता है वही. फिर या रोल तो क्या कहें, वैसे ही ग्रोथ होता है. आप ग्रोथ को ऐसे कंट्रोल करना पड़ेगा कि भाई एक लेयर बन जाए. आपको ग्रोथ को ना इनहिबिट करना पड़ेगा. कोई कैपिंग एजेंट कुछ ऐसा ऐड करके, अगर आप केमिकल सिंथेसिस या किसी रिएजेंट से बना रहे हैं, तो आपको बस सिंगल लेयर बनने के बाद इनहिबिट करना पड़ेगा. अदरवाइज मल्टी वॉल बनने के ही चांसेस ज्यादा हैं. नहीं
सर, जो स्कॉच स्टेप है ना, उसमें हम सिंगल लेयर आराम से बना देंगे.
लेकिन प्रॉब्लम तो ये है ना कॉस्ट स्टेप की, कि अमाउंट तो बहुत कम मिलेगा ना. आप किसी केमिकल मेथड से बनाओगे, जैसे आप लेजर अब्लेशन मेथड से बनाओगे, या वो तो लार्ज स्केल पे मिल जाएगा ना, आपको ग्राम में मिल जाएगा, खूब सारा पाउडर मिल जाएगा जिससे आप बहुत सारे करेक्टराइजेशन कर सकते हैं. मेन प्रॉब्लम तो लार्ज स्केल प्रोडक्शन की होती है ना. आप एक लेयर बना लेंगे लैब में, वो तो सिर्फ स्टडी पर्पज के लिए है. अप्लाई करना है तो आपको लार्ज स्केल प्रोडक्शन चाहिए. विदाउट लार्ज स्केल प्रोडक्शन आप कैसे करेंगे? सिग्मा एल्ड्रिच है, सीएनटी बना के बेच रहा है. उसका रीजन यही है कि वो इलेक्ट्रिक डिस्चार्ज मेथड, या उसमें तो नहीं बनता, लेजर एब्लेशन, पल्स लेजर डिपोजिशन या सीवीडी मेथड यूज करके बनाता है वो, और इसलिए वो बेच रहा है क्योंकि बहुत ज्यादा बना लेता है. आप टेप से कैसे बना के बेचेंगे? वो तो सिर्फ स्टडी के लिए है, लेबोरेटरी पर्पज के लिए. हाँ जी, हेलो. हाँ
हेलो
हाँ, मैं
सर, मल्टीपल नैनो ट्यूब को कंडक्टिविटी भी इंक्रीज हो जाएगा ना?
हाँ हाँ जी, कोई और प्रॉब्लम? किसी को कोई प्रॉब्लम है?
हेलो सर.
हाँ जी बोलो.
हेलो
हाँ जी बोलिए.
सर, ये पूछ रहे हैं कि जैसे मल्टीपल नैनो ट्यूब लेने पर सर इसका कंडक्टिविटी भी तो इंक्रीज हो जाएगा ना सर?
मल्टीवॉल कार्बन नैनो ट्यूब लोगे, डिपेंडिंग अपॉन कि भाई उसमें कितने डिफेक्ट्स हैं, है ना। एक वॉल लोगे तो डिफेक्ट भी कम होगा, कई सारे वॉल लोगे तो डिफेक्ट भी बढ़ जाएगा, है ना। डिपेंडिंग अपॉन कंडीशन कंडक्टिविटी डिपेंड करेगी, लेकिन कंडक्टिविटी ज्यादा तो सिंगल वॉल की ही होगी। जितना बढ़ाते जाएंगे कंडक्टिविटी धीरे धीरे फिर कम होती जाएगी, है ना। डिपेंडिंग अपॉन आपके पास क्या है, टोटली डिपेंड करेगा कि आप कैसा बनाते हैं। लेकिन
यस
ये
सर, लेकिन मेरा सर ये
हम्म,
सर मैं ये सोच रहा हूँ जैसे नंबर ऑफ नैनो ट्यूब्स अगर इंक्रीज करेंगे तो नंबर ऑफ एटम्स जो होंगे उसमें ज्यादा आ जाएंगे, तो इस वजह से उसकी कंडक्टिविटी जो
डिफेक्ट भी
होगी
तो ज्यादा
नंबर
हो
ऑफ
जाएंगे
आयंस।
ना। डिफेक्ट तो
यस
ऑब्स्ट्रक्ट
सर।
करेंगे, आपको पता है कि ज्यादा डिफेक्ट होते हैं तो क्या होता है, करंट को फ्लो नहीं करने देते, वो रोकते हैं, रेजिस्टेंस बढ़ाएंगे, तो ऑप्टिमाइज करना पड़ेगा नहीं। हाँ जी
यस सर, यस सर।
सर मल्टी लेयर नैनो ट्यूब में एक वॉल दूसरे वॉल से कैसे कनेक्ट थी सर? सारे ही सेपरेट नजर आ रहे थे।
मल्टी वॉल में कैसे कनेक्टेड है, वीक वंडरवॉल फोर्सेस ऑफ अट्रैक्शन से। वंडरवॉल फोर्सेस ऑफ अट्रैक्शन जो न्यूट्रल एटम के बीच में लगता है, जिसको मैंने बहुत डिटेल में पढ़ाया कभी तो आप लोगों को, उसी की वजह से वो कनेक्ट होते हैं। आलोक कुमार महंता, अंजना,
Present, sir.
असगर अली,
Yes, sir.
अतुल, ब्रह्मानंद,
प्रेजेंट सर।
अब्दुल,
Present, sir.
दिया,
Present, sir.
इप्सिता,
Present, sir.
कल्पना, किरण,
Present, sir.
कुलदीप,
Present, sir.
मगन। बाकी ये रिसर्च का
Present, sir.
टॉपिक है, आप इसको जितना पढ़ेंगे उतना कम है, ठीक है। मैंने आपको पूरा नहीं बताया कुछ ऐसा, क्योंकि एक लेक्चर में तो इतना ही बताया जा सकता है। मुरली मनोहर,
Present, sir.
नमिता,